Welcome to the Cosmic Wonders channel, where we unravel the mysteries of the universe. Today, we're diving into a remarkable discovery that redefines our understanding of space and time. Get ready to embark on a journey 13.4 billion light-years away. ERS recently celebrated a significant milestone, the anniversary of the James Webb Telescope. This event marks a noteworthy occasion, as this telescope is far from ordinary. The James Webb Telescope, a product of collaboration between NASA, the European Space Agency, and the Canadian Space Agency, stands as the largest and most costly telescope launched at its time. Its journey began on December 25, 2021. Within just a month, it settled into its orbit, positioned 1.5 million kilometers, approximately 900,000 miles, away from Earth. In July 2022, the world got its first glimpse through this remarkable telescope with the James Webb unveiling breathtaking images. Each new revelation from the telescope has been more astonishing than the last, enabling astronomers to make remarkable discoveries. Dear traveler, welcome aboard. Today, we embark on a thrilling voyage through space, led by the groundbreaking findings of this unprecedented telescope. Before embarking on our cosmic exploration, it's essential to grasp what sets the James Webb Telescope apart. This ambitious project spanned over 3 decades. Initiated in 1989, the telescope's journey faced near cancellation in 2011, with its originally planned launch in 2013. The extended timeline was due to immense technological challenges and significant budget overruns. Initially estimated at $3 billion in 2005, the cost soared to $10 billion. The project engaged 10,000 people, with some dedicating their entire careers to its development. The telescope's impressive features include a weight of over 6 tons and a heat shield as large as a tennis court, underlining its extraordinary scale and complexity. Fortunately for the realms of science and astronomy, the James Webb Telescope triumphantly emerged, launching aboard the Ariane 5 rocket on December 25, 2021, from the Kourou base in French Guiana. It was strategically positioned in orbit around the L2 point, 1.5 million kilometers, or 900,000 miles, from Earth on the side opposite the Sun. This specific location is vital for the telescope's survival in space. The launch process was intricate. To fit within the Ariane rocket's 5-meter diameter nose cone, the telescope was ingeniously designed to fold, earning it the nickname Origami Telescope. Its main mirror was segmented into 3 parts, and the sun shield meticulously folded. A tense moment for scientists was when the James Webb had to autonomously unfold in space, a significant departure from its predecessor, Hubble, which received several space missions for repairs. The James Webb's mission duration is initially set for 5 years, with energy reserves capable of sustaining its position at the L2 point for at least a decade. As it fulfills its mission, the telescope is expected to transmit an array of extraordinary images. The significance of the James Webb Telescope lies in its ability to capture images in the infrared spectrum. Infrared radiation, emitted by stars, planets, and galaxies, is essential for comprehending the mysteries of space. However, Earth's atmosphere obstructs some of this radiation, making infrared observations from Earth's surface impractical. NASA's IRIS, an infrared telescope launched into orbit in 1983, served as a pioneering venture in space observation. This set the precedent for the James Webb Telescope. When scientists commenced planning for the James Webb, they aimed to create a highly capable telescope, specifically optimized for infrared observation, drawing inspiration from IRIS's groundbreaking work. The launch of the James Webb Telescope marks a pivotal step in space exploration. Its mission is multifaceted. It will delve into the mysteries of the earliest galaxies formed just after the Big Bang, studying their diversity and formation. Additionally, it will examine exoplanets and their atmospheres, searching for biosignatures that might suggest extraterrestrial life. The telescope is also set to observe Sagittarius AE, the black hole at the center of the Milky Way, supplementing the images captured by an array of telescopes in May 2022. The James Webb Telescope was conceptualized as a successor to the Hubble telescope, which was launched on April 24, 1990. Unlike Hubble, which primarily focuses on visible light, the James Webb's 4 scientific instruments are adept at capturing infrared light. This feature becomes crucial when studying distant celestial bodies. On March 3, 2016, Hubble captured an image of the galaxy Gien's 11, located 13.4 billion light-years away, the most distant galaxy ever observed. However, it appeared only as a vague red spot due to the phenomenon of redshift, where the expansion of the universe stretches the light waves, making distant galaxies appear redder. In contrast, closer objects with compressed light waves tend to appear bluish. While Hubble can detect some infrared waves, its capacity is limited to observations not more than 500 million years post-Big Bang. Designed to extend the boundaries of our celestial understanding, the James Webb Telescope is equipped to see deeper into the infrared spectrum and consequently further back in time. Its observations focus on near and mid-infrared wavelengths ranging from 0.6 to 28 micrometers. Unlike the Hubble telescope, it cannot capture ultraviolet light or the entire visible light spectrum. To effectively capture the elusive light of ancient galaxies, the James Webb is positioned 3,000 times farther from Earth than Hubble, orbiting around the Lagrange point. This strategic location is critical for infrared observations, as it helps avoid interference from the telescope's own heat emission or from the thermal energy of the Earth, Sun, and Moon. Without its sun shield, the side of the telescope facing these bodies could reach temperatures up to 110 degrees Celsius, 230 degrees Fahrenheit. However, its design and orbital position maintain its temperature around minus 240 degrees Celsius, about minus 400 degrees Fahrenheit. If the sun shield were likened to sun cream, it would have a protection factor of 10 million. Infrared observations offer a window into the universe's history, aiding astronomers in advancing our understanding of space. This includes studying the formation of the earliest stars and galaxies post-Big Bang, the processes driving galaxy evolution, the genesis and composition of supermassive black holes, and the makeup of exoplanet atmospheres. Astronomers have invested immense effort in unraveling the mysteries of the universe, and the James Webb Telescope stands as a testament to this dedication, showcasing a marvel of technological innovation. Equipped with a massive 6.5-meter, 21 feet diameter mirror, it is designed to focus incoming light. This is complemented by 3 imagers and a spectrograph, which capture and analyze the light. These sensitive measurement tools require a cool environment to function optimally and are shielded by an enormous sun shield as large as a tennis court. In its unique orbit, the telescope circles the Lagrange point at a velocity of 1 kilometer per second, completing a full orbit in 6 months. It also mirrors Earth's journey around the Sun, completing a solar orbit in 365 days. Just over a year since its launch, the James Webb Telescope has surpassed all expectations. It has unveiled extraordinary images of nebulae and distant galaxies, displaying a clarity and quality never seen before. Additionally, it has captured unprecedented images of planets within our solar system, like Jupiter and Neptune, with unparalleled precision. Astronomers are thrilled, as the James Webb has operated without technical issues, and its instruments have proven to be even more effective than anticipated. The images produced by the James Webb, which we are about to see, are typically invisible to the naked eye since they are in the infrared spectrum. Astronomers have colorized these images to make them accessible and appreciable to the general public. The first image from the James Webb Telescope was released on July 12, 2022. It shows the galaxy cluster ESCS 723 as it appeared 4.6 billion years ago. NASA described it as the deepest and sharpest infrared image of the distant universe to date, a historic achievement. However, it's not the deepest image ever captured, considering the Planck satellite's photograph of the cosmic microwave background in 2013, which contains the universe's oldest photons. Returning to the James Webb's first image, ESMA-CS 723 is a dense cluster of galaxies over 4 billion light-years away. The area photographed is astonishingly small, no larger than a grain of sand. Remarkably, this image reveals 19 galaxies, in contrast to the 5 observed by Hubble. More than just a display of precision, it also demonstrates the phenomenon of gravitational lensing, a concept of general relativity described by Albert Einstein. This effect refers to the deflection of light by a massive object, such as a planet, galaxy, or cluster of galaxies. In practical terms, gravitational lensing occurs when a massive celestial body lies between an observer and a distant light source. This phenomenon deflects the light rays passing near it, thereby distorting the images received by the observer. Due to this lensing effect, in the first James Webb image, 14 of the 19 galaxies are seen in triplicate, 2 are quadrupled, and 1 is even quintupled. This initial image from the James Webb Telescope, sharper and more detailed than any provided by Hubble, could assist scientists in determining the ages and masses of star clusters within distant galaxies. This information is crucial for developing more precise models of these galaxies, as they existed in the cosmic springtime, a period in the distant past when galaxies were actively interacting, merging, and before expanding into larger spiral forms. Following this first deep field image, the telescope has continued to unveil new discoveries. One significant finding involves the exoplanet WASP-39b. The data from the James Webb indicates the presence of CO2 in its atmosphere. This represents not only the most detailed analysis of an exoplanet's atmosphere to date, but also the first ever detection of CO2. WASP-39b, located 700 light-years away in the Virgo constellation, is a hot gas giant similar to Saturn and has a quarter of Jupiter's mass. WASP-39b orbits its star even closer than Mercury does to our Sun. When the exoplanet transits in front of its star, the stellar light filters through its atmosphere, enabling scientists to analyze the spectrum and determine its chemical composition. Carbon dioxide was identified in this way, marking the first detection of this molecule outside our solar system. However, despite the association of carbon dioxide with life, WASP-39b is clearly uninhabitable, being a gaseous planet with temperatures exceeding 870 degrees Celsius, almost 1600 degrees Fahrenheit. This discovery excites astronomers as it demonstrates the possibility of detecting CO2 on planets beyond our solar system, particularly on rocky exoplanets with characteristics more akin to Earth. Moreover, James Webb didn't just detect CO2 in WASP-39b's atmosphere, it also found sulfur dioxide, so too another first for an exoplanet. This SO2 is believed to originate from a photochemical reaction caused by high-energy photons from the star, a process similar to photochemistry on Earth, which is a key component in photosynthesis. Additionally, James Webb observed other unique features of this exoplanet. The clouds in its atmosphere appear fragmented rather than forming a uniform cover. WASP-39b's atmosphere is devoid of methane and hydrogen, but contains sodium, potassium, and water vapor. These observations are vital for advancing our understanding of the chemistry that shapes the atmospheres of exoplanets. Astronomers are hopeful that by gaining insights into the atmospheric evolution of exoplanets, they can develop models for the formation and evolution of these celestial bodies. Based on data from the James Webb Telescope, scientists have pieced together the formation history of WASP-39b. It appears to have originated from the collision and amalgamation of small rocky bodies, eventually evolving into an exoplanet. Over time, the planet moved closer to its star. On July 12, 2022, the James Webb Telescope also sent back an image of the Carina Nebula. In the colorized photograph, it resembles a mountainous landscape dotted with glittering stars. In reality, this is a young, star-forming region within the Carina Nebula, known as NGC 3324. Although previously photographed by Hubble, the images captured by the James Webb Telescope are much more precise. A nebula is an interstellar cloud comprised of gas and dust. They are classified based on their luminosity. Emission nebulae emit light from their gases, while reflection nebulae reflect the light of nearby stars. Additionally, there are dark nebulae, which remain unilluminated. Until the 1920s, the term nebula was broadly used to describe any celestial object with a diffuse appearance. However, scientists later realized that some objects appeared diffuse only due to the limitations of observational instruments. Since this realization, nebula specifically refers to regions in the interstellar medium with high concentrations of gas or dust. Nebulae often form from the remnants of supernova explosions, which scatter debris across the universe, forming a gas and dust cloud, known as a nebula. The Carina Nebula, located 7,600 light-years from Earth, is visible in the southern hemisphere sky. It functions like a stellar nursery, where stars are continually born and perish. NASA recently announced a significant find within the James Webb's image of the Carina Nebula, particularly young stars, whose study could enhance our understanding of the processes leading to the formation of stars like our Sun. The precision of the image even allows us to observe the dust disks that prelude the emergence of a star. In nebulae, the gravitational pull causes gas and dust to coalesce, forming a sphere. This sphere of gases spins rapidly, increasing in temperature, leading to a nuclear reaction. This process transforms the gas ball into a star. On September 12, 2022, the James Webb Telescope captured a remarkable image of the Orion Nebula, also known as Messier 42 or M42, the nearest nebula to Earth. Located approximately 1,350 light-years away in the Milky Way, the Orion Nebula is visible from Earth using a telescope or refractor. With binoculars, one can even observe the trapezium cluster, the brightest section of the nebula. The colorized photograph taken by the James Webb shows the Orion bar, a dense wall of gas and dust within the nebula, in exceptional detail. The two brightest stars visible in the image, located just in front of the Orion bar, belong to the trapezium cluster. These stars, which formed in the Orion Nebula around 300,000 years ago, are hot and massive. Their intense ultraviolet radiation dramatically affects the surrounding environment, eroding the Orion bar and clearing away the less dense filaments. Previous images from the Hubble telescope depicted the area less clearly, but with James Webb's advanced capabilities, it's evident that the brightest stars of the trapezium cluster have carved a vast cavity in the nebula. The James Webb achieves such precision by observing in the infrared spectrum, allowing it to peer through layers of dust, obscuring the nebula. The image also reveals a star cocoon with a protoplanetary disk 40 times the size of the distance between Earth and the Sun. These conditions are akin to those that led to the formation of our Sun and planets 4.5 billion years ago. Thus, the imagery of the Orion Nebula, much like that of the Carina Nebula, is crucial for understanding the formation of our solar system. This significance is heightened by the fact that when the universe was half its current age, starburst galaxies, which are rich in nebulae, were the most prevalent type of galaxies. Echoing the captivating imagery of the Orion Nebula, NASA released another spectacular nebula image on September 6, 2022. This time, it was the Tarantula Nebula, also known as 30 Doradus, situated 161,000 light-years from Earth in the Large Magellanic Cloud dwarf galaxy. The Tarantula Nebula stands as the largest and brightest star-forming region in our neighboring galaxy group. It hosts some of the hottest and most massive stars known. In this celestial locale, stars are born at an astonishing rate. The Tarantula Nebula is of particular interest to astronomers due to its chemical composition, reminiscent of the immense star-forming regions observable when the universe was just a few billion years old, during the zenith of star formation. The image from the James Webb Telescope, using its NIRCom, near-infrared camera, uncovers thousands of young stars previously hidden. While Hubble had photographed this nebula before, many of these stars, veiled in dust, remained unseen. At the center of the image is the nebula's cavity, featuring a cluster of massive young stars shimmering in blue. This cavity has been sculpted by the energetic winds of these stars, which push back the material from which they were born tens of thousands of years ago. Surrounding this cluster, the densest dust regions conceal protostars still in the process of formation. Similar to the images of the Carina Nebula and the Orion Nebula, this image of the Tarantula Nebula is anticipated to provide astronomers with deeper insights into the mechanisms of star formation. There's yet another nebula image to explore: the Southern Ring Planetary Nebula, also known as NGC 3132 or Caldwell 74, which was released on July 12, 2022. Planetary nebulae were initially mistaken by astronomers for planets, hence their name. These expansive clouds of gas are the result of giant stars nearing the end of their life cycles. As these stars become unstable, they begin to expel their outer layers. Planetary nebulae typically dissipate within 50,000 years or less, a brief period considering that dwarf stars like our Sun have an average lifespan of about 10 billion years. While the odds of observing planetary nebulae might appear quite slim, in reality, they are more common than one might think, given the vastness of our galaxy, which boasts between 200 and 400 billion stars. As a result, we have identified over 1,500 planetary nebulae. The Southern Ring Planetary Nebula, situated approximately 2,500 light-years from Earth within the constellation of the Veils, provides an excellent example. Thanks to the remarkable precision of the James Webb Telescope's images, scientists have discerned that this planetary nebula isn't solely the product of a single dying star. Rather, it is the outcome of a binary star system. In this binary system, the second star, which shines brighter than the dying star at the nebula's core, now a white dwarf, exerts its influence on the nebula's appearance, shaping the surrounding gas and dust into distinctive asymmetric patterns. The second star is also enveloped in dust, implying that it, too, will eventually give rise to a planetary nebula when it reaches the end of its life. Scientists are eagerly anticipating images from the James Webb Telescope that might capture the rare phenomenon of a nebula within a nebula. However, it's worth noting that this second star could continue to exist for several million more years, making it unlikely that we'll witness this event in our lifetimes. In the meantime, we continue to be captivated by the astounding landscapes revealed in images from the James Webb Telescope: spectacular arcs of matter, shrouds of dust, and tendrils emitted by stars in the process of formation. The James Webb Telescope was meticulously designed to advance research across various domains. It will significantly enhance our understanding of starbirth, the intricate processes involved in the formation and evolution of exoplanets, and much more. However, one of its primary missions is to capture the light of the earliest galaxies, those that emerged shortly after the Big Bang. By observing these primordial galaxies, astronomers aspire to glean insights into not only the formation and development of galaxies, but also the universe as a whole. This mission was beyond the capabilities of the Hubble telescope. The James Webb, with its near and mid-infrared vision, can peer further back in time to study the nascent galaxies and investigate objects that remain concealed from the Hubble, hidden behind dense clouds of dust. To execute this mission, the James Webb has been equipped with 4 cutting-edge scientific instruments, 3 of which operate in the near-infrared spectrum: the NIRCom, the NIRSPEC spectrograph, and the NIR-IR spectroimager. Additionally, one instrument functions in the mid-infrared range, the MIRI spectro-imager. MIRI, in particular, plays a crucial role, complementing the capabilities of the other instruments, despite its nearly unrealized existence. The possibility of such an instrument was considered at the inception of the James Webb Telescope's design project in the early 2000s. At that time, astronomers were primarily focused on the near-infrared spectrum. But why is it of paramount importance for astronomers to seek out the most ancient galaxies? The reason lies in the potential revelations they hold about the cosmic dawn, a distant epoch in the early universe, when the cosmos emerged from the abyss of darkness, giving birth to the first stars. The Big Bang, the birth of our universe, is believed to have occurred approximately 13.7 billion years ago. This monumental event was followed by an extended period of cosmic darkness, during which the universe gradually cooled. Around 100 million years later, driven by the force of gravity, matter began to coalesce in certain regions, sparking the formation of the first stars. These stars, in turn, played a pivotal role in shaping the earliest galaxies. However, the intriguing question remains: how did these transformations in our universe unfold? What were the fundamental physical processes that governed these cosmic evolutions? These are the profound inquiries that astronomers grapple with, seeking answers that will illuminate the origins of our world. The images and data delivered by the James Webb Telescope have not only met, but exceeded the expectations of astronomers. What's more, these observations have presented astronomers with profound challenges to their prior understanding of the earliest galaxies. Firstly, the information gleaned from the James Webb data indicates that the formation of the very first galaxies occurred earlier than previously anticipated. Additionally, these galaxies appear to be both more numerous and more radiant than astronomers had envisioned. The models astronomers had relied upon did not predict such luminous and abundant galaxies at this early stage of the universe's history. The traditional view of the early universe held by astronomers was one of chaos and turbulence. However, the observations made by the James Webb Telescope paint a different picture, revealing that the earliest galaxies were surprisingly organized and serene. These observations pose a significant challenge to the current understanding of galaxy formation. The prevailing model posits that at the genesis of galaxies, dark matter halos played a crucial role. These halos would attract ordinary matter, such as hydrogen gas, which would subsequently condense and give rise to the first generation of stars and galaxies. However, this model struggles to account for the rapid and abundant formation of galaxies witnessed by the James Webb. Among the ancient galaxies scrutinized by the James Webb, several stand out for their remarkable brightness. These galaxies are among the oldest ever observed, dating back to a mere 450 to 350 million years after the Big Bang. For instance, Jade's GSZ 13.0, situated at a staggering 33 billion light-years from us, could be considered the oldest galaxy, originating just over 300 million years after the Big Bang. This discovery challenges the long-held record held by GN's 11, which emerged 400 million years after the Big Bang. But how is it possible for Jade's to be so distant when the universe itself is only 13.8 billion years old? The light we perceive from Jade's has traveled for 13.6 billion years, allowing us to witness the galaxy as it existed 300 million years after the Big Bang. However, due to the expansion of the universe, smaller than our own Milky Way, these galaxies possess a remarkable ability to swiftly convert gas into stars. This phenomenon presents a compelling mystery for astronomers. How could these ancient galaxies, seemingly quite massive, have generated such an abundance of stars in such a short span of time? According to current models, star formation in these galaxies would have commenced a mere 100 million years after the Big Bang. Alternatively, it's possible that these galaxies harbor what are known as population 3 stars, which differ from the stars we are familiar with on Earth. These elusive population 3 stars, though purely theoretical, have never been directly observed. Another revelation brought forth by the James Webb Telescope is that these ancient galaxies do not possess the irregular shapes suggested by Hubble's previous images. Instead, they showcase magnificent spiral structures reminiscent of our own Milky Way. Astronomers perceive this as a unique opportunity to gain deeper insights into the processes of star formation, further substantiating the notion that these galaxies are still in their infancy. Measurements from the NIRSPEC instrument indicate that the primitive galaxies captured by the James Webb are remarkably devoid of metals, being approximately 100 times less enriched in metals than our Milky Way. It's worth noting that these metals are generated within stars themselves. At the pinnacle of the most distant galaxies ever observed lies Glasses 13, a discovery made by the James Webb Telescope in July 2022. By measuring the redshift of Glass 13, astronomers have determined that it resides at a staggering distance of approximately 13.4. This galaxy has drawn the attention of astronomers. The NIRCom instrument on the James Webb Telescope was instrumental in detecting Glass 13. It was observed within the deep field, a broader image captured with extended exposure time to capture the faintest of celestial glimmers. The resulting image has been transformed into a visible spectrum, revealing a blurred red circular shape with a white center. The precise time frame of Glass Z13's formation remains uncertain. Astronomers are grappling with the enigma of how such a massive galaxy could emerge so swiftly in the cosmic timeline, mere moments after the Big Bang. Among the researchers behind the discovery of Glass Z13 is Peter Van Dokken, known for his work on unraveling the mysteries of ultra-diffuse galaxies. The existence of these stars challenges established theories, prompting astronomers to reevaluate their understanding of galactic formation and evolution. Galaxies, the majestic cosmic structures we observe, are believed to have originated from dark matter, a concept notably theorized by Nobel Prize-winning physicist James Peebles. Peter Van Dokken, reflecting on the time when Glass Z13 was observed, noted that the universe was only 2.5% of its current age. This observation, although pending confirmation, hints at the possibility that the formation of massive galaxies may have commenced much earlier in cosmic history than previously conceived. Speaking of galaxies, the James Webb Telescope has set its sights on an exceptionally intriguing one galaxy, M74, also known as Messier 74 and affectionately dubbed the Ghost Galaxy. This moniker arises from its notably low surface brightness, making it challenging to discern. M74, a splendid spiral galaxy with well-defined spiral arms, resides at a distance of 32 million light-years from Earth in the Pisces constellation. Unlike some other spiral galaxies with irregular structures, M74 boasts a distinctive design. Its discovery can be credited to the French astronomer Pierre M. Chain in 1780 and later observations by Charles Messier, from which it derives its name. While Hubble had previously ventured to photograph this galaxy, the resulting images were somewhat lacking in clarity. However, the images captured by the James Webb Telescope, released on August 30, 2022, and artfully recomposed by amateur astronomer Judy Schmidt, who has also delved into the realms of Jupiter, have presented a new level of precision. The James Webb Telescope, with its ability to pierce through the veils of gas and dust, has unveiled astonishingly clear images of the galaxy's core, shedding light on hitherto unknown aspects of this celestial wonder. Specifically, we can observe the graceful spiral arms of M74, adorned with delicate filaments of gas and dust, gracefully unfurling outward from the galaxy's core. However, in the central region, there is a noticeable absence of gas. It's in these regions of pronounced luminosity that star formation takes place, aptly named HIE regions. These are, in reality, vast clouds of hydrogen gas, their brilliance ignited by the radiant ultraviolet emissions from young, scorching stars embedded within. A single image captures a rich tapestry of celestial features. The aging stars don a reddish hue, predominantly found toward the center, while the youthful, vibrant stars, adorned in blue, grace the spiral arms. Interspersed among these, the stars in the making manifest as crimson bubbles within the HII regions. This remarkable visual spectacle promises to invigorate astronomers in their relentless pursuit to fathom the enigmatic processes governing the birth of stars and galaxies. The James Webb Telescope has also unveiled a mesmerizing portrayal of a galaxy already known but never before observed with such precision and clarity: the Chariot Wheel Galaxy. Nestled 500 million light-years away within the Sculptor constellation of the Southern Hemisphere, this galaxy derives its name from its captivating wheel-like structure. A composite image skillfully merging observations from James Webb's MIRI and NIRCam instruments has not only deepened our understanding of this galaxy's genesis, but also offered a glimpse into its future evolution. Astronomers speculate that it might have initially existed as a spiral galaxy, akin to our Milky Way. Then, approximately 400 million years ago, it underwent a high-speed collision with a smaller neighboring galaxy, ultimately shaping its distinctive wheel-like appearance. This cosmic collision resulted in the formation of two concentric rings at the heart of the galaxy, reminiscent of ripples emanating from a pebble dropped into water. The innermost ring, radiating intense brightness, unveils vibrant star clusters that were previously concealed by veils of gas and dust, as observed in Hubble's earlier images. The outermost ring, expanding for a staggering 440 million years, owes its growth to collisions with the ambient gas. These encounters trigger violent compressions of matter, setting the stage for the birth of new stars. The outermost ring, expanding for a staggering 440 million years, owes its growth to collisions with the ambient gas. These encounters trigger violent compressions of matter, setting the stage for the birth of new stars. The remarkable precision of the James Webb Telescope's imagery extends beyond the confines of our primary subject, revealing intricate details of distant galaxies scattered across billions of light-years. Among the initial images unveiled by the telescope, we encounter the captivating Stephan's Quintet, a collection of 5 galaxies situated within the Pegasus constellation. Their discovery dates back to 1877, credited to observations made with the telescope at the Marseille Observatory. Within this group of galaxies, gravitational associations link 4 of them, namely NGC 7317, NGC 7318A, NGC C7319b, and NGB CZ 7319. These 4 celestial neighbors reside at a distance of approximately 290 million light-years from Earth. However, the 5th and brightest member, NGC 7320, appears deceptively close to the others. In reality, it occupies a foreground position relative to the quartet, positioning itself a substantial 40 million light-years away from Earth. The striking image before you is the result of merging 1,000 distinct graphic files, rendering it the most intricate depiction of Stephan's Quintet to date. Among the quartet of associated galaxies in Stephan's Quintet, NGC 7319 stands out as a subject of keen interest for astronomers. This galaxy harbors an active galactic nucleus, boasting a luminous energy output equivalent to 40 billion times that of our Sun. This prodigious energy source emanates from a supermassive black hole at the galaxy's core, weighing in at a staggering 24 million solar masses. To put this into perspective, consider that the supermassive black hole at the heart of our Milky Way galaxy measures slightly more than 4 million solar masses. The medium-resolution spectrometer of the James Webb Telescope's MIRI instrument has provided crucial measurements of the gas in the vicinity of NGC 7319's central black hole. Upon scrutinizing the spectra near the black hole, it becomes evident that the gas in the vicinity is cooler and denser, particularly within the reservoir of the black hole, namely the gas reserves situated at the periphery of the accretion disk. These gas reserves contain substantial quantities of molecular hydrogen and silicate dust, which serve to absorb light originating from the central regions of the galaxy. Remarkably, these silicate dust particles possess a composition akin to beach sand, albeit with grains significantly smaller than those of ordinary sand. Furthermore, the gases in this vicinity are hot and ionized, featuring the presence of elements such as iron, argon, neon, sulfur, and oxygen. This wealth of information holds significant promise for astronomers, as it will enable a deeper understanding of the properties and origins of the plasma flows surrounding the black hole. Leveraging the precision of the Stevens Quintet images, astronomers are poised to investigate the intricate dynamics and interactions between these galaxies. One of the images that left a profound impact on the public's imagination is famously known as the Pillars of Creation. The sheer beauty of this image, adorned with captivating shades of blue, red, and gray, explains why it holds such fascination. But what exactly are the Pillars of Creation? The Pillars of Creation first gained widespread recognition through a Hubble image back in 1995. They represent a region of active star formation located approximately 6,500 light-years away in the heart of the Eagle Nebula, scientifically cataloged as Messier 16. The Eagle Nebula stands as one of the Milky Way's most prolific star-forming regions. Thanks to the James Webb Telescope's remarkable infrared capabilities, we've been afforded yet another glimpse into this celestial wonder. The telescope's advanced vision allows us to peer through the veils of gas and dust, revealing an area densely populated with both stars and intricate gas and dust formations. In fact, when comparing the James Webb image to its Hubble predecessor, one can't help but notice the remarkable difference. The James Webb image unveils a plethora of stars, even more numerous than what the Hubble image had disclosed. These stars, appearing as vibrant red dots, are essentially cosmic infants, with ages spanning just a few 100,000 years. Additionally, the red streaks apparent within the dust and gas clouds are nascent globules of gas that are destined to evolve into new stars. And that's not all. Another image, captured by the MIRI instrument, offers a different perspective on these iconic pillars of creation, sometimes poetically referred to as the Pillars of Destruction. Why is this so? The distinctive shape of these colossal columns of dust can be attributed to the relentless erosion inflicted upon them by the ceaseless onslaught of ultraviolet radiation emanating from young, massive stars. It's a process that ensures these dust columns have a relatively short-lived existence. In the captivating image captured by the MIRI instrument, one may notice a conspicuous absence of brilliantly shining stars. This is due to the instrument's sensitivity being limited to specific wavelengths, precisely in the range between 5.6 and 25.5 microns. At these wavelengths, stars emit negligible amounts of light, rendering them nearly invisible. Instead, the MIRI image primarily unveils a cosmic tapestry of gas and dust, interwoven with the presence of youthful stars enshrouded within their protective cocoons of gas and dust. Amidst this celestial tableau, there are also stars that have shed their gossamer veils, appearing as radiant blue points of light against the backdrop. These high-resolution images of the Pillars of Creation hold immense significance for astronomers and scientists alike. They provide invaluable insights that will enable the refinement and updating of models pertaining to the intricate process of star formation. The James Webb Telescope has graced us with exquisite images of Jupiter, its moons, its magnificent rings, and the mesmerizing auroras that dance across its polar skies. These highly precise images promise to deepen our understanding of this colossal planet, a celestial giant that could effortlessly engulf 2.5 times all the other planets in our solar system. The creation of this awe-inspiring image owes its existence to the data collected by the James Webb's Near-Infrared Camera, or NIRCam. Expertly processed and adapted for public consumption, the image is a testament to the telescope's capabilities. In this visual masterpiece, different colors signify distinct wavelengths of light. The regions bathed in resplendent red hues represent the longest wavelengths, while areas adorned in striking blue embody the shortest wavelengths. Adding to the enchantment, the mists enveloping Jupiter's north and south poles have been artistically rendered in shades of yellow and green. A reddish filter highlights the ethereal auroras and the radiant reflection of light by the lower clouds that grace Jupiter's majestic atmosphere. Furthermore, a serene blue filter portrays the gentle glow emanating from the deeper layers of Jupiter's dominant cloud cover. Jupiter's auroras, a phenomenon of exceptional beauty and scientific intrigue, are birthed from the interaction of charged particles originating from the Sun with Jupiter's formidable magnetic field. These charged particles engage with the atoms and molecules in the planet's atmosphere, eliciting a mesmerizing display of light across a spectrum of specific wavelengths. It is Jupiter's magnetic field that masterfully funnels these charged particles towards its polar realms, where they manifest as enduring auroras, in stark contrast to the transient auroras seen at Earth's poles. Of particular note are the most energetic of Jupiter's auroras, which owe their existence to matter ejected from its moon, Io. Electrons and ions, including sulfur and oxygen, escape Io's grasp and are ensnared by Jupiter's magnetic embrace. Here, they harmonize their rotation with the planet's own majestic spin, accumulating along Io's orbital path. Their eventual escape gives rise to a mesmerizing procession of waves, electric currents, and magnetic reconnections, culminating in the breathtaking display of Jupiter's auroras. A study conducted in August 2021 illuminated the pivotal role of these auroras as a celestial radiator, contributing warmth to the entire planet. As for the rings that encircle Jupiter, they grace the image with their presence, albeit in a subdued and understated manner, casting a muted glow amidst the celestial splendor captured by the James Webb Telescope. According to NASA, these rings are 1,000,000 times less luminous than the planet itself. Additionally, the image provides a fascinating glimpse into the tempestuous winds and storms that sweep across Jupiter's surface. Among these features, the Great Red Spot stands out prominently, although it appears white in the image due to the abundant sunlight it reflects. However, in reality, it is an immense storm of colossal proportions, capable of engulfing the entire Earth. The Great Red Spot is a colossal anticyclone within Jupiter's atmosphere, boasting winds that howl at speeds exceeding 700 kilometers per hour, or more than 435 miles per hour. Its dimensions are nothing short of astonishing, spanning approximately 15,000 kilometers, 9,300 miles, in width and nearly 12,000 kilometers, 7,500 miles, in length. Remarkably, this iconic storm has been a fixture of Jupiter's skies for over 350 years, having been first observed in 1665. While its name suggests a vivid red hue, the Great Red Spot's color has evolved over time, transitioning into a more subdued brownish tone. Within the same image, two of Jupiter's 79 moons make a subtle appearance, Amalthea and Adrastea. These diminutive moons are exceedingly small and present quite the challenge to discern. Shifting our focus within our own solar system, the James Webb Telescope has treated us to an extraordinary view of Neptune's rings, marking the most detailed observation in over 3 decades. Not since the Voyager 2 spacecraft's historic encounter with Neptune in August 1989 have we enjoyed such a clear and vivid portrayal of Neptune's delicate ring system. On September 21, 2022, the telescope unveiled a series of captivating images of the ice giant Neptune. These images are especially significant because they represent the first time we have had the opportunity to observe Neptune's rings in the infrared spectrum. However, there's an intriguing surprise within these images. Neptune, typically associated with its striking blue hue, appears predominantly white and gray in the James Webb Telescope's infrared gaze. Neptune exhibits its iconic blue hue when observed in visible light, a characteristic attributed to the presence of methane in its atmosphere. Consequently, images captured by the Hubble Space Telescope depict Neptune in its familiar blue splendor. However, the James Webb Telescope, operating in the near-infrared spectrum, presents Neptune in a distinct palette of white and gray. Beyond the revelation of Neptune's exquisite ring system and its enigmatic color transformation, this remarkable image divulges additional surprises. Positioned at one of Neptune's poles, NASA identifies an intriguing phenomenon as strange light, adding a layer of mystique to the planet's features. Furthermore, the James Webb Telescope's keen eye has captured the presence of 7 of Neptune's 14 moons, including Triton, which might initially be mistaken for a small star within the image. Astonishingly, Triton eclipses even the dwarf planet Pluto in terms of size, rendering it highly conspicuous in the image. This prominence is attributed to Triton's capacity to reflect an impressive 70% of the sunlight that graces its surface, owing to its composition of nitrogen ice. Among the other moons visible in the images are Glacier, Naiad, Thalassa, Larissa, Proteus, and Spina, contributing to the rich tapestry of Neptune's moon system. Astronomers have received these images with great enthusiasm, as Neptune poses unique challenges for observation. Its vast distance from the Sun, being approximately 30 times farther away than Earth, results in an environment cloaked in relative darkness. Additionally, our understanding of the 8th planet in our solar system is primarily informed by a single space mission in NASA's Voyager 2 probe, which conducted its historic exploration of Neptune in 1989. This mission significantly expanded our knowledge of Neptune, leading to the discovery of its intricate ring system. Nevertheless, Neptune remains an enigmatic celestial body, harboring a plethora of unresolved mysteries. Notably, a peculiar dark spot detected by the Hubble Space Telescope on December 15, 2020, continues to baffle scientists. Initially thought to be a storm, this dark feature exhibits unconventional behavior that defies easy explanation. Astronomers are keen to unravel the secrets concealed within this celestial enigma. Another point of intrigue revolves around Neptune's moons, which exhibit behavior that is often unpredictable and intriguing. NASA has conducted a study focused on 2 of Neptune's small moons, Naiad and Thalassa, which engage in a captivating orbital dance of avoidance. These moons maintain an intricate orbital resonance, and their peculiar orbits raise questions that astronomers are eager to answer. Furthermore, there exists a tantalizing hypothesis that within the depths of Neptune, diamonds may be raining from the heavens. Confirmation of this extraordinary notion could provide new insights into the unique planetary conditions present on Neptune. The upcoming discoveries made possible by the James Webb Space Telescope hold the promise of shedding light on these unresolved mysteries. More recently, the James Webb Space Telescope has provided compelling evidence of a rocky exoplanet known as LHS 475b, situated 41 light-years away from our solar system. This exoplanet shares several intriguing similarities with our own Earth, sparking the curiosity of scientists and astronomers. One of the most striking resemblances is its size, as LHS 475b boasts a diameter that is approximately 99% that of Earth's. However, despite these resemblances, significant differences come to light upon closer examination. While its temperature is only slightly warmer than Earth's, it still experiences temperatures several hundred degrees higher, placing it closer in comparison to Venus than Earth. This heightened temperature is attributed to LHS 475b's exceptionally close proximity to its star, LHS 475, which is a red dwarf. Despite being twice as cold as our Sun, the data collected by the James Webb Telescope indicate unusually high temperatures on this exoplanet. Currently, 2 main hypotheses have emerged to explain the unique conditions on LHS 475b. The first hypothesis suggests that this exoplanet may lack a substantial atmosphere altogether. Alternatively, it is posited that LHS 475b's atmosphere could be composed entirely of carbon dioxide, CO2, in stark contrast to Earth's atmosphere, which contains only a small fraction of this gas. In fact, the spectroscopic analysis indicates a high probability of an atmosphere devoid of the typical components found on habitable planets. The discovery of LHS 475b was made possible through the collaborative efforts of the James Webb Telescope and another astronomical instrument, the Transiting Exoplanet Survey Satellite, TESS. Launched in 2018, TESS is equipped with 4 wide-field cameras designed to survey the celestial heavens, measuring the brightness of distant stars. The initial hypothesis of this exoplanet's existence arose from TESS's observations, which detected a periodic decrease in the brightness of its host star. James Webb further confirmed the presence of LHS 475b using the transit method, which involves meticulously observing the exoplanet as it passes in front of its host star, causing a discernible dimming of the star's light. This remarkable discovery highlights the power of collaborative efforts within the realm of space exploration and our ongoing quest to unveil the mysteries of distant exoplanets. You might be curious about why it took a year for James Webb to detect this planet. The reason is quite straightforward. James Webb's observing time is exceptionally valuable, and its field of view is relatively small. Consequently, it cannot remain fixed on a single region of the sky for extended periods in the hopes of capturing an exoplanet's transit event. When an exoplanet passes in front of its host star, creating a phenomenon known as a transit, there is a noticeable reduction in the star's brightness. This dimming serves as a crucial indicator of the presence of an exoplanet. Fortunately, additional observations are scheduled for the summer of 2023, offering astronomers the opportunity to uncover more details about LHS 475b. Key questions that scientists hope to address include whether this small rocky world possesses an atmosphere, and if so, what that atmosphere is composed of. Furthermore, there is curiosity about the potential for this exoplanet to provide a suitable environment for extraterrestrial life. In any case, the discovery of LHS 475b by the James Webb Space Telescope is already a promising achievement. It signifies the telescope's capability to detect other rocky exoplanets, expanding our understanding of the cosmos. Additionally, a photo released by James Webb in November 2022 unveils the intriguing formation of a protostar, adding to the telescope's growing list of remarkable discoveries. L1527 is situated in the Taurus constellation. The light emanating from this youthful star, which is approximately 100,000 years old, takes on a distinctive hourglass shape, earning it the moniker Smyk hourglass. The formation of this hourglass is a result of material being expelled from the nascent star. As this material moves away from the protostar, it interacts with the surrounding matter, creating cavities. At the center of this cosmic hourglass, we can observe the protoplanetary disk, a rotating disk of gas, also known as an accretion disk. This disk supplies the protostar with the material it needs for growth, forming a horizontal bar that partially conceals the star in the image. According to NASA and ESA, this image of L1527 offers a glimpse into what our Sun and solar system might have looked like during their early stages. L1527 is in the earliest phase of star formation, where nuclear fusion has not yet commenced. Astronomers possess models that detail what comes next in the star formation process, and the observation of L1527 will serve to validate these models. In the near future, this young star will accumulate mass, undergo compression, and experience a rise in core temperature, eventually reaching the point where nuclear fusion ignites a moment when a new star is born. We've embarked on a journey through the remarkable discoveries made by the James Webb Telescope, and it's undeniably impressive. Astronomers are more than pleased with the outcomes achieved by the James Webb. Many images have substantiated existing hypotheses, And there's a keen desire to delve even deeper into detailed observations to enhance our understanding of galaxy, birth, and star formation. The James Webb's 2023 program is already bustling with activities. Notably, the telescope will direct its focus towards objects in the Kuiper Belt. The Kuiper Belt is a ring-shaped region in our solar system, extending beyond Neptune's orbit, spanning between 30 and 55 astronomical units. Although resembling the asteroid belt in shape, it is considerably wider and more massive, containing icy remnants from the solar system's formation, including dwarf planets like Pluto and Haumea. Astronomers aim to investigate the atmosphere's composition of these Kuiper Belt objects, especially by scrutinizing the sunlight they reflect. In 2023, the James Webb Telescope will also examine the black hole at the center of the Milky Way, known as Sagittarius AA, and the Iris Nebula. The Iris Nebula, or NG C7023, is situated 1,300 light-years away from Earth in the constellation of Cepheus. It's categorized as a reflection nebula, a cloud of dust that reflects the light of one or more nearby stars. Reflection nebulae often coincide with regions of active star formation, adding to the intrigue for astronomers. Furthermore, within this nebula, scientists have detected peculiar phenomena, including the formation of giant fullerene molecules composed of chains containing 60 carbon atoms, a surprisingly complex occurrence for such an environment. Finally, some astronomers are hopeful that the James Webb Telescope can contribute insights to the enduring scientific debate that divides the community. There exists a vibrant discourse within the scientific community, with some firmly advocating the existence of dark matter, while others explore alternative hypotheses. Among the proponents of alternative theories is the Monday theory, which posits that the laws of gravity and mechanics must undergo modification to comprehensively describe the origin and behavior of galaxies. The Monday theory, or modified Newtonian dynamics theory, stands as an alternative to the concept of dark matter. It was first introduced in the 1980s by Israeli physicist Mordechai Milgram and is presently championed by Stacy McGaugh of Case Western Reserve University in Cleveland, USA. This theory offers a potential explanation for the rapid formation of ancient galaxies detected by the James Webb Telescope, a phenomenon not yet accounted for by the standard cosmological model. Most importantly, James Webb holds the promise of furnishing us with genuine insights into the formation of our universe. This is because the telescope can observe objects that emerged a mere 100 million years after the Big Bang, enabling astronomers to delve even further into the early history of the cosmos. Someday, it may offer answers to the profound mysteries surrounding the initial moments of our universe. Welcome to Blasovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blasovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe. Live Q and a sessions with experts. Your membership will grant you the chance to participate in Live Q and a sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blasovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment